Okay, so in the previous two sessions, we have mostly practiced the numerical problems based on psychometry, and now we will try to slightly move towards. So, before even going to the air conditioning system design, few psychometric processes only. I'll try to specify some generic system which is also very popular sometimes to achieve different psychometric processes, and then slowly we will shift towards the air conditioning system design. Okay, but before that we have one very important equipment which is called as air washer. Okay, and within the air washer all the psychometric processes, for example, heating and humidification, heating and dehumidification, cooling and dehumidification. Okay, all these processes can be achieved. Okay, so what typically we have air washer, and other than that, whenever you have studied your applied thermodynamics, or particularly the thermodynamics studied subject, or even energy conversion devices, whenever you are talking about maybe in that subject about the coal based thermal power plants which are based on Rankine cycle, have you ever come across with the term cooling tower? Did you heard term cooling tower? Any one of you have seen near a power plant a very tall cylindrical structure out of which fume, white colored fume is actually coming out? Have you seen near to a power plant? So that is nothing but a cooling tower. Okay, first let us study about the air washer, then in order to just make the similar context I will briefly explain you the cooling tower. Okay, so typically air washer is a insulated vessel, and in this insulated chamber we are having certain arrangements with the help of which actually we can achieve different processes. In the inlet of this insulated chamber we have some filter, and the purpose of this filter is that whenever I will be allowing air to flow over this filter, it will be actually removing all the dust particles which are present in the air. Other than that, whenever I am at the outlet of the chamber, near the outlet of the chamber, again I am having certain arrangement, and this arrangement is particularly called as eliminator over here. So I'll be doing certain things in this chamber which will be leading, which may lead to carry over of small sized fine droplets along with the air. So we need to actually avoid the motion of these droplet along with the air. So that's why some eliminator plate we are actually using over here. Then in the bottom we have a sump. In this sump typically we have water, and in order to maintain the constant level of the water we use over here some float valve as well. So we are having some float valve arrangement, and from here we supply the makeup water. Is this one here? So from here typically we supply the makeup water. Now in this what we have a pump. We have a pump which takes the water from the sump, and that water is then passes through a coil, and this can be a heating or cooling coil. Is this one clear? And from this, whatever the water is coming, that water over here, with the help of nozzles, we create a water spray. So spray of water droplets in the form of very fine droplets. So here you can see that these all represents nothing but fine spray of water droplets. Is this one clear? Now let us consider that m dot a amount of air is coming here. Of course m dot a amount of air will be going out of this. Let's consider its initial enthalpy was H1, temperature was T1, and humidity was W1. When this air is going out, its enthalpy is H2, temperature is T2, and humidity is W2. Okay. Now let's consider that water at the rate of MW is actually sprayed in this one. And when this water is sprayed, at that time let us consider its temperature was TW1. And when this water has moved down, particularly when it is coming out of the chamber, then its temperature is say TW2. Is this one clear? So water temperature at the inlet to the nozzle is TW1, and below it is, which is coming out of the sump, it is TW2. Is this one clear? Now, in this particular device is called as air washer. Now, depending upon the different temperature conditions, whenever we will be doing the analysis, we will be finding that different processes we can achieve with the help of the single device. Okay. One of the easiest process which we can achieve in this, that process is nothing but adiabatic saturation process. Okay. What is the meaning of adiabatic saturation process? You have some water, that water you will be actually spraying from the bottom. Spraying from the top. So whenever you are spraying the water from the top, and if chamber is perfectly insulated and you are not doing any heating or cooling of the water, what will happen? Some portion of water will be actually evaporating and temperature of air will decrease. And you can also see that whatever this air will be now, if air washer is of infinite size, then air at the exit must be nothing but saturated air. Is this point clear? All are clear with this point or not? It's like whenever I defined you the adiabatic saturation temperature, wet bulb temperature, what we were having? We were having a long pool, and over the pool air was actually flowing. So same type of process will happen. Now even additional thing we are doing, that we are spraying the water in the form of fine droplets, so that the energy exchange between the air and the water can increase. Okay. And if this process happens, then you will be finding that ultimately what will happen? If this was my state 1, if I am doing adiabatic saturation process, then if my air washer is of infinite size, then I must move along a constant wet bulb temperature line, and I must reach to point 2s. Okay, I will be able to reach point 2s when my size of the air washer is infinite. But if size is not infinite, then I will be stopping somewhere over here. Say this is my some state 2D. Okay. Now, if I define efficiency of the process can simply be defined as T1 minus T2D, actual change in temperature, divided by whatever the temperature change would have occurred if I would have infinite amount of size. So that is T1 minus T2s. Is this one clear? Similarly, this efficiency can also be written in terms of the change in humidity. So corresponding humidity values if I define. Is this one clear? So that is the efficiency. So the point is very clear that if I am only having the water, and that water without any heating or cooling process I am just spraying, then ultimately it will be behaving like a adiabatic saturation chamber. Okay, air washer will be behaving like a adiabatic saturation chamber, in which cooling and dehumidification process will take place. Why cooling? Because when air is getting saturated, some amount of liquid is converting into vapor, and that heat is coming from the air, because process is adiabatic. So that's why cooling will happen, and at the same point of time humidification will happen. All agree to this point? But other than only this process, this particular device is even important for achieving different type of psychrometric processes. By just controlling the temperature of water, we can achieve different type of processes in this. Okay, so to understand all these processes which we can achieve, let us first do the energy balance across this. So if I take this as a control volume, this is my control volume. So in this control volume, what is happening? M dot A amount of air is coming with enthalpy H1. So I can say that M dot A is coming with enthalpy H1, Other than that, you can see over here m dot w amount of water is coming, and it is coming with what temperature? TW1. Considering it to be in the liquid state, I can write plus m dot w CPW into TW. Correct? This is the energy coming. What is the energy going out? Energy going out is m dot A, and with how much enthalpy it is going? H2. Other than that, you can also see that from the bottom, I have a pump which is taking some amount of water. What is that water? That let us understand. From the top, how much amount of water I have sprayed? M dot W. Out of this m dot W, some amount of water has evaporated, and it got added in the form of water vapor to the moist air. How much is the amount of water vapor evaporated? M dot A into W2 minus W1. This is the amount of water evaporated. So how much amount of water is now entering into the sump? M dot W minus M dot E, which is equal to M dot W minus M dot A into W2 minus W. Correct? Whenever this water is moving in downward direction, this water now will not come at temperature TW1, because in between this water has also exchanged the heat with the air and the cool water. Okay, so after it has exchanged heat with air and cool water, its temperature now has changed from TW1 to TW. Is this one clear? So I can say that plus m dot W minus m dot A into W2 minus W1 amount of water is coming, but it is coming at temperature TW2, so it will be CPW into TW. Correct? All are clear with this point or not? Okay. Now, from this, if I little bit do algebraic manipulations, I will be finding m dot A into H2 minus H1 will be equal to m dot W into CPW TW2 minus TW1 minus of m dot A into W2 minus W1 into CPW TW2. Up to this point, anyone is having any doubt? All are clear with this point? So this is the, let me give this equation as equation number 1. We will be coming back to this equation again. So this is the generic equation of the air washer. Okay, is this one clear? All are clear with this point or not? Now let me make the assumption of adiabatic saturation condition. What is the meaning of adiabatic saturation? Let me see, m dot A into H2 minus H1 equal to, sorry, yes, TW1 minus TW2, correct. And this will be plus. Is this clear? Now, if I assume the process of adiabatic saturation, what it means? It means that I am not doing any heating or cooling of the water. If I am not doing any heating or cooling of the water, then water temperature before pump and after pump must be same. So TW1 must be equal to TW2. For adiabatic saturation, this point must satisfy. If this is the situation, then I will be getting that m dot A into H2 minus H1 will be equal to m dot A into W2 minus W1 CPW into TW2. And ultimately I can simply write that H2 minus H1 equal to W2 minus W1 into CPW into HW2 can be written as enthalpy of fluid, water, HF. Is this one clear? So this is the equation number 2 is nothing but equation of adiabatic saturation process, where state 2 in a adiabatic saturation process will be nothing but saturated state. Is this one clear? Now, using this equation, if I define H2S star, say my 2S is nothing but the saturated state corresponding to state 2, which will be giving me wet bulb temperature. So H2 star must be equal to H2 plus W2S star minus W2 into HF2 star, and similarly I can write H1S star equal to H1 plus W1S star minus W1 into HF1 star. Star is state corresponding to saturated condition. Okay, and that saturated condition how we have achieved adiabatically. Because saturated condition I can achieve by two ways. One is by cooling at the constant pressure. If I achieve by cooling at the constant pressure, then final temperature at saturated state will be dew point temperature. Okay, and second state I can achieve saturated state from unsaturated state by using adiabatic evaporation. So if I do that, then whatever the final temperature I will be getting, that is called as wet bulb temperature. If you recall, on the TS diagram I have plotted something like this. From state A I can come to state D, which will be dew point, and other I can come like this, which will be wet bulb temperature. Correct? So I am talking about the process A to B from one end, state 2. All of you agree to this point? Okay. Now what I will be getting, let us make two assumptions now. Let us assume that HF1 star is nearly equal to HF2 star. This is my very first assumption, that HF1 star is nothing but nearly equal to HF2 star, and second assumption is W2S star is nearly equal to W1S star. Is this one clear? So I have made two assumptions over here. These are just assumptions, that whenever in process 1 to 1S or 2 to 2S I am achieving the saturated condition, whatever the water I am supplying, its enthalpy is almost same. Okay, and humidity of the final saturated state is also same. If I do so, and if I subtract these equations, I will be getting H2S star minus H1S star is equal to what? H2 minus H1 plus or minus of W2 minus W1 into HF. Is this point clear? Will I be getting this equation or not? Equation number 3. Now carefully look, equation number 3 and equation number 1. Do you have some similarity? Equation number 1 and equation number 3. Do you have some similarity? Please tell me. W2 minus W1 into HF. This is the term, and other term is m dot A into H2 minus H1. So m dot A into H2 minus H1 minus of m dot A into W2 minus W1, if I do, then I will be getting that this term must be equal to m dot A into this term. Are you able to see this similarity or not? Take this term to the other side. If you take it to the other side, it will be becoming m dot a into h2 minus h1 minus of w2 minus w1 into cpw into tw2, which is this term. So then this, whose left hand side is this, and this, these two must be same. Is this one clear? So from 1 and 3, what I can write, from 1 and 3, I can say that m dot a into h2s star minus h1s star must be equal to what? M dot w cpw into tw1 minus tw2. This is one very important equation. Now you consider the case. If tw1 is greater than tw2, what it means? h2s star is greater than h1s star. Are you getting my point or not?
Yes.
If tw1 is greater than tw2, then h2s star is greater than h1s star. What it means? It means that enthalpy of adiabatic saturation process for state 2 will be greater in comparison to state 1. This H2S star is nothing but a direct function of T2S star and T1S star, which is nothing but my wet bulb temperature. So I can simply say that if my water temperature is hot, then wet bulb temperature T star at 2 will be greater than T star at 1. So during this process, wet bulb temperature will be actually increasing. Is this point clear or not? Getting my point or not? So it means wet bulb temperature of the fluid, of the moisture, will be increasing from T1 star to T2 star. Is this one clear? So if I have to represent this process on psychrometric chart, how I can represent? Now let's go to graphical form. This is dBT, this is W, say this is my state 1. What I have done? I have added hot water. So it's very clear, when I am adding hot water to air, what will happen? Temperature of air will also increase. And this equation is also telling us that my wet bulb temperature of state 2 will be more in comparison to wet bulb temperature of state 1. So generally, this is how my constant wet bulb temperatures lines are drawn. And when I move towards the upper side, then wet bulb temperature value is more in comparison to the lower one. So that's why my process must move in which direction? In this direction. And that will be my state 2A. Is this one clear? So 1 to 2A process is possible when TW1 is greater than TW2, and in this process wet bulb temperature of state 2 is greater than wet bulb temperature of state 1, which is clear from the corresponding saturation enthalpy states. Okay. Second condition is if TW1 equal to TW2. In this scenario, what this equation is giving? This equation is telling that this will be 0, H2S star equal to, which must be equal to TW2 will be equal to, T2 star must be equal to T1 star. Is this point clear? So what will happen in this process? Enthalpy and wet bulb temperature must remain same. What is the meaning? I must move along a constant wet bulb temperature. So this will be up to line 2s. Fine. And of course, in real scenario, instead of 2s, I may end up somewhere over here. I will be naming that process soon. What is third situation? Sorry, I must not write 1 to 2a. Let me write 1 to 2s. What will be third situation? TW1 is less than TW2. In this scenario, what will happen? Okay, this is the scenario. So in this process, cooling and humidification will take place, but it will take place in such a way so that the temperature must decrease. Okay, so it means like this. I will be getting some line like this. Is this point clear? So these are the different conditions which we have seen. Now one by one, let us see that what are different processes which we can achieve in air washer. First process is heating and humidification. And heating and humidification process is process 1 to 2a. Okay, so see, if in the air washer I have to heat air and I have to increase its humidity also, what I need to do? I need to supply water at temperature greater than the temperature of the air. Then only it will be gaining heat from the water. Okay, so TW1 must be very large so that I can heat the air at the same point of time I can increase the moisture also. Okay, so the necessary condition is that TW1, which is the water inlet temperature, that must be greater than the inlet temperature of the air, T1. For achieving heating and humidification, my water temperature must be greater than temperature of the air. Temperature at 0.1. Okay, because then only that air will be gaining the heat. And process 1 to 2a represents, because when you go from 1 to 2a, then your temperature as well as the humidity both are increasing. So it means necessary condition is that whatever the water we are spraying, its temperature should be greater than T1. So it means after the pump, whenever I am supplying water, I need to switch on the heaters so that I can supply heated water to the nozzle. Point is clear? Number 2, pure humidification. When pure humidification will be happening?
Same.
Let me see process 1 to 2b. If I move along the constant line. Okay? What should be the necessary condition? Only humidification should happen. So the necessary condition is TW1 must be equal to T1. TW1 must be equal to T1, and anything else? Okay, let's stop with this. That is pure humidification. All are clear with this point or not? The next process, cooling and humidification. 1 to 2c. And let us consider whatever this cooling and humidification process I am doing, for this process TW1 is less than T1. TW1 is less than T1, but it is greater than T1 star. What is the meaning? The meaning is water temperature is in between the dry bulb temperature and the wet bulb temperature. In this scenario, what will happen? Of course, because dry bulb temperature is greater in comparison to water temperature. Okay, so air can supply heat to water, cooling will happen, and wet bulb temperature, which leads to adiabatic saturation condition, that is less in comparison to water temperature. So it means moisture can also come in. So that's why the process will be represented something like this. It means it will be above the constant temperature line. All are clear with this point or not? Agree? Process number 4. Again cooling and humidification. But in which manner? Adiabatic manner. And let me name process as 1 to 2D. In this case, what must happen? T1 star must be equal to TW1. Whatever the water which we are supplying, if it is already at the wet bulb temperature, then ultimately what will happen? The process will take place along the constant wet bulb temperature line, 1 to 2s, and of course the actual point will be somewhere over here, 1 to 2. Is this one clear? Fifth process. Again cooling and humidification. I have to do cooling also, I have to do humidification also. In this case, let me name the process 1 to 2E. In this process, TW1, which is water temperature, it is less than T1 star. It means it is less than wet bulb temperature, but it is more than TD1. What is D? Dew point temperature. Clear? It means my temperature is less than wet bulb but greater than dew point. So greater than dew point ensures that always there will be humidification. No moisture will be condensing because temperature of water is greater than dew point. But it is less than wet bulb. So if it is less than wet bulb, then the cooling will take place in such a way so that the process must be below the constant wet bulb temperature line. Okay. So process will be something like this. This will be process 1 to 2. Is this one clear? See, you have to understand all these points are conceptually very strong actually. Okay. How? By just controlling the temperatures you can achieve all these different processes. Next process. Sensible cooling. 1 to 2F. What I am doing? Only cooling. How it will be possible? If my water temperature is equal to dew point temperature, what will happen? If water temperature is equal to dew point temperature, then whatever the excessive moisture will be there in the air, that excessive moisture will be condensing. Okay. So, and the process, how it will be moving? This will be my process 1 to 2F. Because dew point is at this point. See, dew point for state 1, how we define dew point temperature on psychrometric chart? We draw a horizontal line and whenever it touches the saturation state, corresponding to that, whatever is the temperature, that is my TD1. That is the dew point temperature for state 1. So if I say that my water is at dew point temperature, and if heat transfer process is not 100% efficient, then the actual process, it means air which is at this state and water is at this state, somewhere in between this I will be getting my final state. So it will be a pure sensible cooling process. Is this one clear or not? Process number 7. Cooling and dehumidification. What is the meaning? Cooling will also happen and temperature will also go. Temperature is also going down and humidity will also decrease because dehumidification. So if my water temperature is less than dew point temperature, what it means? Now water is even at less than dew point temperature. So whenever air will be exchanging heat, once its temperature goes below the dew point temperature, immediately what will start happening? Condensation of the moisture will start happening and that will lead to dehumidification of the air. Okay. So I will be having something like this. So this will be process 1 to 2G, and of course the actual temperature is of water is less in comparison to dew point temperature. So all the different type of psychrometric processes can be done with the help of a single device which we are calling as air washer. Okay, by just controlling the temperature of the water with reference to the temperature of the incoming air. All are clear with this idea? Now I told you one term, cooling tower. Okay, so can any one of you tell me the similarity between the cooling tower and air washer? Okay, first tell me what is the purpose of cooling tower? Why we use cooling tower? See, I told you that we are dealing with thermal power plant. Okay, in thermal power plant, what is our aim? To produce power. To producing power, we are working on a heat engine cycle. In heat engine cycle, we have to reject some amount of heat. So in Rankine cycle, what we do in the condenser, we remove certain amount of heat. For removing that certain amount of heat, typically we study that we use ambient water. Okay, lake water or something. It is many times in the it is given in the question that we are taking water from the lake at the flow rate of this. Okay, so it means we are taking water from the lake. So wherever close to thermal plant I have water body, there it's very simple. You take water from the river, exchange heat, and then again dump the water into the same river. But in the areas where do not have such abundant amount of water available, okay, we have scarcity of water, there what we do? We take a reservoir, from that reservoir we allow the water to flow through the condenser. Whenever water will be flowing through the condenser, its temperature will be increasing. But again, if I have to supply the same water to the condenser, then its temperature must be brought down to the original atmospheric temperature. So that's why cooling tower is a big tower in which from the top we actually spray large amount of water droplets, whatever is coming from condenser outlet. And then we have a fan at the top. Of course, there are different types of cooling towers. Some are induced draft, forced draft, some are natural draft. So natural draft size is a bit larger, where the density difference is governing the flow. In forced draft, there is a fan at the inlet which supplies the ambient air in upward direction. And in induced draft, one fan is at the top of the cooling tower, which actually continuously takes the air from the bottom and it keeps on moving that air in the upward direction. When that air is moving in upward direction, from the top you have sprayed the water droplets. These water droplets comes in contact with water and it leads to the process of cooling and humidification. That's why from the top of the cooling tower you see white fume is coming out. It means that air is almost in the saturated state. So significant amount of water vapor it contains. Okay. So when that water is evaporating, in that process air and remaining portion of the water is actually cooling. So at the bottom of the cooling tower that cold water is collected and that cold water is then again recirculated to the condenser. Okay. And nowadays even if you have water body available close to the power plant, then also you have to actually use cooling tower, because whenever you dump the hot water into the water body, it creates thermal pollution. Okay, because of thermal pollution, whatever the ultimately water body temperature will increase. So whatever the species which are present in that water body, these will be actually dying down. Is this point clear? So the purpose of cooling tower is clear. Whereas the purpose of air washer is what? To control the state of the moisture. Okay. So purpose of cooling tower is to cool the water. Purpose of air washer is to control the state of that. But overall mechanism is same, because there also water is sprinkled from the top and then air is allowed to come in contact with that. So here also in air washer also physical configuration is same, and even the different psychometric processes which are taking place, these are also same. The only difference is in the purpose which we are trying to achieve from that particular device. Is this point clear? So air washer is having very close similarity to that of cooling tower which we use in thermal power plants. Okay. Now there is one very important term which is called as adiabatic dehumidification. Can you tell me what is adiabatic dehumidification? If you have to dehumidify something and you don't want to exchange any heat, okay, so you all might have heard that there are certain materials, for example silica gel and activated alumina. Okay, what characteristics these have? What are their characteristics? Whenever you pass water vapor through these quickly absorb or adsorb. These adsorb water vapor. Okay, these will be absorbing water vapor. So what you can simply do, you can take silica gel. Say I have a rotating wheel. In this wheel I have some porous structure on which silica gel or activated alumina, any device is there, and I am just rotating this wheel, and from the front I am allowing air to flow over this. What will happen? Whatever the moisture I will be supplying, it will be trying to capture the moisture out of it, and it will try to decrease the humidity. Okay, so usually if I draw a psychrometric chart, then this is my constant wet bulb temperature line. So this is constant WBT line. Okay, typically if I start from state 1, then what will be happening? My moisture will be absorbed. So moisture will be absorbed in adiabatic fashion. So I must move along this line, because I am doing it in an adiabatic fashion. Okay, so I must move along this line, but ultimately instead of this I end up somewhere over here. What is the reason for rise in slight shift away from the adiabatic line? That shift is due to the fact that this adsorption of water vapor, this process is actually exothermic. So being exothermic, it releases certain amount of heat. Okay, and that heat leads to heating of the air. So slight heating of air takes place in this adiabatic dehumidification process. Is this one clear? However, you have to remember one point, that if you have to practically implement this, then whatever the rotating wheel I have taken, if I simply kept on passing the air, then after some time all its porous sides will be filled with water vapor and it will not be able to further capture the moisture. So what I need to do? I need to again activate it. In order to activate it, whatever the moisture is collected at its sides, I need to remove it. Okay. So practically how it is achieved? So typically we define a outer chamber which contains some sector. In half of the sector we pass the room air which we want to process, whose moisture I want to decrease, and in remaining portion we pass the outside ambient hot air which actually removes the moisture, because hot air will be having tendency to capture more and more moisture, so it captures the moisture from the silica gel porous structure and then it actually removes it. Okay. So this process is called as adiabatic dehumidification. Sometimes in the air washer we not only spray the water, but along with the water sometimes we also spray some other solutions like ethylene glycol, etc. after mixing it in certain concentration with the water. What is the reason? The reason is because whenever we mix ethylene glycol, etc., then freezing point decreases, and at the same, so we can use air washer even for low temperature application. Other than that, even for above 0 degree Celsius also sometimes we add these. The reason is addition of ethylene glycol, etc., decreases the water vapor pressure at a given temperature. Okay, is this one clear? So if it decreases the vapor pressure, then the potential for transfer of vapor from the moist air actually increases. So more rapid transfer of vapor takes place. Maybe just a practical thing I am explaining to you, will not discuss that part in detail. Okay, is this one clear? Now after this, quickly we will shift towards the air conditioning system design. Whenever we do the air conditioning system design, one important law comes into picture, and of course that law comes in even psychrometric processes as well, and we need to keep that law in mind, because based on that only we will be able to analyze our entire air conditioning systems. Okay, so that law is called as straight line law. In order to understand this law, let us assume that we have a cooling coil. Usually what happens in the AC? What happens in the AC? Have you seen the window AC? In the window AC, there is some coil like this. Okay. Inside that coil, what is happening? Refrigerant is flowing in the evaporator, and over that coil you have some arrangement like this. What are these? These are fins, and then in the cross flow direction room air is actually circulated over this, and when it moves over this coil, then it leads to different processes. Okay, cooling and humidification, heating and humidification, sensible cooling, pure humidification, depending upon the type of process which we want to achieve. Is this point clear? Anyone is having any doubt about this? Now let us understand one very important principle. Let us consider that whatever the cooling coil we have and all its fin structure, everything is, say, this is my duct, and in this duct, this is the portion of this cooling coil and its fins. And when air is entering to this duct, let us consider that all the air is having very perfect contact with the each and every surface of the fin and the cooling coil. Is this one clear? And the cooling coil temperature is less than the dew point temperature. So if I represent this process on psychrometric chart, what will happen? Whenever the air is coming, say air was at state 1, whenever it is coming in full contact, immediately it will be cooled. I will be having cooling process from 1 to 2. And then let's consider that its temperature is less than dew point temperature. Then after this point, what will start happening? Dehumidification. So dehumidification along this line. And if this was my temperature of the cooling coil, let's consider T3 is temperature of cooling coil. And I am saying that everything, I am having everywhere the perfect contact. So if I am having perfect contact, I will be able to achieve this process. Is this point clear? Now let's come to the practical considerations. If I come to practical considerations, first point is for heat and mass transfer to occur, there should be some potential available. What is potential for heat transfer? Do you have class? Okay, then we will discuss in the next class.